Welcome to the Explainer. So, have you ever actually stopped to wonder what it takes to power a ship the size of a skyscraper? Well, today, we're taking a highly structured visual journey through a truly definitive engineering text, D.K. Sanyal's Principles and Practice of Marine Diesel Engines. We're going to deconstruct this book chapter by chapter to unlock the secrets of massive maritime power. Let's dive right in. We're looking at the ultimate blueprint of maritime power here. Our goal today is to completely demystify exactly what's hiding inside this cover. We're going to break down the complex thermodynamics, the incredibly precise fuel injection systems, and the extreme mechanical balancing required to safely power global shipping. Okay, here's our roadmap for today. 1. Core thermodynamic cycles. 2. Engine testing and load. 3. The fuel injection system. 4. Variable injection timing. And finally, 5. Mechanical loads and balancing.
So let's jump right into part 1, core thermodynamic cycles.
All right, going all the way back to Rudolf Diesel's 1893 patent, we really have to look at the foundational theory first. Now, what's really interesting here is the stark contrast between the two dominant thermodynamic cycles. On the left, we've got the PV, or pressure volume diagram, for the Otto cycle, and right next to it, the diesel cycle. If you look at the shape of those curves at the very top of each graph, that difference, right there, is the literal secret to massive diesel power. So, what does this all mean? The absolute crucial point is exactly how heat is added. You see, in the Otto cycle, heat is added at a constant volume. But our practical marine engines, they lean heavily on the diesel cycle, where heat is added at a constant pressure. Because of this mathematical quirk in their efficiency equations, the practical diesel engine can pull off way higher compression ratios. I mean, a diesel engine operating at a compression ratio of 14 is just fundamentally more efficient than an Otto engine stuck at a ratio of 7. But, here is where pure theory meets salty reality. Slow-speed marine engines don't actually follow the pure diesel cycle to the letter. They actually utilize what's called an air standard dual cycle. It's kind of like the best of both worlds. It combines the advantages of those previous cycles by adding heat partly at a constant volume and then partly at a constant pressure. This mixed cycle lets the engine manage those insane peak pressures while still keeping specific output and thermal efficiency incredibly high. Let's move on and see how this builds in part 2, engine testing and load. Okay, so before a massive cargo ship is ever cleared to head out to sea, engineers have to define its MCR, or maximum continuous rating. Basically, this is the absolute maximum continuous output that the engine can run out safely, day in and day out. Establishing this specific baseline is absolutely crucial because literally every single calculation for the mechanical strength of the entire engine is built on this one number. And based on that MCR, engineers map out the performance curve of a two-stroke engine. They use this super complex load diagram during testbed trials to figure out the exact limits of continuous operation. If you trace the lines, it's pretty amazing. You can see exactly how they map safe operation against variables like fuel oil consumption, exhaust temperatures, and scavenging air pressure. But hey, an engine doesn't just operate in a vacuum, right? It's physically attached to a massive propeller. And that brings us to the propeller law, which dictates that power is proportional to the cube of the speed. Think about that for a second. It means you can't just crank up the engine speed without matching the physical demands of the propeller. If you try to push the engine speed while the ship is, say, fighting a rough sea or dealing with a fouled hull, the propeller simply won't allow it. You'll end up dangerously overloading the engine.
All right, turning to part 3, the fuel injection system.
This is the mechanical heartbeat of the whole operation. Here, the vital needle valve lift and the scroll-type fuel pump below it use intense pressure to rapidly atomize fuel directly into the combustion chamber. That's what gives you a nice uniform burn. The whole system is brilliantly designed so that the pipeline pressure drops instantly the millisecond injection terminates. This accommodates variable loads while keeping the actual rate of fuel admission perfectly consistent. So, how in the world do engineers ensure this injection happens at the perfect microsecond? Well, they use a really clever mechanical procedure called the spill method to accurately check and set the timing. It's a very hands-on physical process. First, you remove the delivery valve. Then you turn the camshaft to its base circle on the compression stroke. Next, you open the fuel lever, and then you just slowly turn the camshaft until the fuel overflow completely stops. The exact angle you read on the flywheel at that exact moment, that determines your injection timing. It's brilliant.
Next up, part 4, variable injection timing.
And this brings us to VIT, or variable injection timing. This is a system that automatically advances fuel injection timing when the engine is in mid-load ranges. By advancing the timing early, the engine can maintain its maximum cylinder pressure even when it's not running at full tilt. This was a real game changer in engineering, honestly. It allows engines to save massive amounts of fuel, and it dramatically controls NOx emissions, all completely automatically. But sometimes the fuel itself is the wild card. And that's where tuning flexibility and the fuel quality setting, or FQS, come into play. When a ship has to take on poor, slow-burning fuel, it causes a big ignition lag, which basically drains power and wastes fuel. Using the FQS, engineers can manually advance or retard the ignition angle. They can essentially tweak it to restore maximum cylinder pressure based on the exact quality of the fuel they're burning that day. Moving to our final stop, Part 5, Mechanical Loads and Balancing. Now, engineers have to contend with two totally distinct types of forces here. On one hand, you have massive static loads. That's just the sheer inert structural weight of things like the bed plate and cylinder block. But on the other hand, you have incredibly violent dynamic loads. We're talking about the inertia, the vibration, the couples produced by heavy moving parts that are constantly threatening to tear the whole engine apart from the inside out. And this brilliantly illustrates what happens when materials are subjected to those relentless forces and extreme temperatures over a long period. This is the curve for creep. It shows how material permanently, plastically deforms under constant stress. Looking at the primary, secondary, and tertiary stages mapped out here, it becomes pretty clear. If those dynamic forces aren't strictly managed, the engine's metal will literally stretch until it reaches the point of total fracture. Definitely not good. So, to prevent catastrophic vibrations and creep, these engines have to undergo meticulous balancing to mitigate those dynamic loads. The engineering objectives are incredibly strict here. You absolutely must balance all revolving and reciprocating masses. You have to counteract inertial forces and couples. The ultimate mathematical goal? You need to ensure the sum of the moments of all masses about the center of rotation equals exactly zero, no exceptions. To pull this off with revolving masses, engineers take the massive crankshaft, which is usually made by joining forged or cast crank throws together, and they attach strategically calculated counterweights directly opposite the crank pin. This precise addition of mass counteracts the unbalanced rotation, and it achieves perfect rotational harmony within the engine casing. Ultimately, what diving into D.K. Sanyal's text reveals is that a marine diesel engine is, well, it's a masterpiece of balanced chaos. It's this highly regulated balancing act where immense thermal efficiency, microscopic fuel timing, and extreme physical forces are all kept in perfect zero-sum harmony. So, I want to leave you with this thought. Next time you look out at the horizon and spot a massive cargo ship slowly making its way across the water, ask yourself, how many perfectly timed microscopic mechanical explosions are happening right now, flawlessly balanced against thousands of tons of steel just to move that ship across the ocean? It's just incredible engineering. Thanks so much for joining me on this explainer, and keep learning.